Hi everybody, this is Jim Corkins, and we are continuing on with motion in 2 dimensions. So if you haven't done the reading, please do so. And this is going to be specifically about projectile motion. Okay? Now we're going to go ahead and ask you a question here. All right, well, moving right along, here we go. I would like you to take a moment and think about this question. Suppose you fired a bullet, and you're firing from a gun, and it's 200 miles an hour, super fast, and somebody is going to drop a cannonball, right? And these cannonballs weigh, I think I remember picking up one, and it was super heavy. It was about, I want to say 70 or 80 pounds. Anyways. And it was a larger cannon. Anyway, so you're going to shoot a ball that weighs 70 or 80 pounds, and you're going to drop a ball that is 70 or 80 pounds, and you're going to do this exactly at the same time. Now, I want you to think about the question, and and it's from a pretty good height. So let's say a 4-story building, and I want you to tell me which one is going to hit the ground first. Okay? The dropped bullet, the fired cannon, or the fired bullet, or will they hit the ground at the same time? So I want you to think about this and vote with what you believe is going to happen. Please pause the video now. Okay, well, I have a video that's ready, and we're going to go ahead and go to it right now. So this part's gonna drop the ball. And the other part is gonna shoot the ball. Let's see what happens when they are shot and dropped at the same time. This is in slow motion. So from that video, what we just found out is that as long as the balls are shot at the same time, both balls will hit the ground at the same time. They will hit the ground together at the same time. This dropped ball will fall down to here, and this shot ball will take a trajectory or parabolic motion and move down that way. Okay. Not quite like that, but you get the point. Okay? Now, the reason why this happens is you've actually already done this in a tutorial, which we are going to do right now. We're only going to do a couple of them, just something real quick, but this is a good one to do. Okay? Now, here we're given this, and it starts off at 0 seconds, and it goes from 0 to 1 seconds, 1 to 2 seconds, 2 to 3 seconds, 3 to 4 seconds, and 4 seconds to 5 seconds. Okay? And this should be just 1 to 2 seconds, and this should be 4 to 5 seconds. Okay. Anyways, so let's go ahead and see what's going on. Now, it's really weird how this works out. It looks like if you look at the velocity vector in the x direction and compare it for all the velocity vectors in the x direction, what you find out is that the velocity in the x direction is constant. they're moving over at 2 meters per second, as long as they're in free fall and there is no air friction. Okay, and everything that we do in this class is in free fall. All right, but in the y direction, it starts out with 1, now it's dropping by 2, and now the velocity vector is 3, and now it's 4, and now it's 5. So this is going to be negative 1 meter per second. This is negative 2 meters per second. This is negative 3 meters per second. This is negative 4 meters per second. And this is negative 5 meters per second. So at each one of these points, and we'll just do 2 meters per second to the right for the blue guys, 2 meters per second to the right for the blue guys, 2 meters to the right for the blue vector, 2 meters per second, and positive 2 meters per second. Okay? Now, if you stack up all those x direction vectors, they look like this. And if you stack up all those y direction vectors, they look like this. And so you've seen this type of motion before. This blue motion is constant velocity. But in the y direction, notice it's increasing its vector size for every vector by 1 second, right? So this is, again, this is negative 1 meters per second, and now it's negative 2 meters per second, and now it's negative 3 meters per second, and now it's negative 4 meters per second, and now it's negative 5 meters per second, okay? While all of these are just positive 2 meters per second, okay? So I'm just going to copy these over here. So you've done this tutorial before. Oh. You've done this tutorial before. I'm just going to, I can't do two things at one time, so I will just hold on before I make a discussion. And I'm going to change the time period because it seems like it's miscounting. And this is from 3 seconds to 4 seconds. So anyways, so what is happening in the x direction is there is no acceleration in the x direction at any point. It's traveling at a constant velocity. That means it can't have an acceleration vector. But in the y direction, you can see it's adding a negative 1 meter per second for every second. So that is a constant acceleration. So what you find out when you look at what we just did here and look back at this question, these two problems are, these two bullets are actually the same bullet. They're both speeding up in the y direction. They just look different, but they're actually the same thing. I should have drawn this vector longer. While in the x direction, this guy does have x direction, it's traveling at a constant velocity. So in the y direction, they have the same motion. So it seems that the time of flight is completely dependent on the y direction motion, or the height that is dropping from. Okay? So what you find out is when a ball is launched horizontally, its initial velocity in the y direction is 0. although it has a constant velocity in the x direction the whole time. And its acceleration vector in the y direction is down at 9.8 meters per second squared. Okay, so it's basically those problems that we did back in one-dimensional motion, and it was the very end of the module where we were only dealing with stuff moving in the y direction. And it just happens to have x direction motion that is constant velocity. Okay, so let's do some problems knowing that when launched horizontally, its initial velocity be in the y direction, it's got a constant velocity in the x direction, and it's accelerating down the whole time at 9.8 meters per second squared. We're going to do problems, and we're going to follow that motion, that procedure that we did before. Okay, it's the same procedure. It hasn't changed. Okay, right? The only thing that has changed in this case with projectile motion is it's accelerating down at 9.8. Okay, but let's do a problem, and hopefully this will help us with the following the procedure. Okay, so just like we did before with the procedure, there are now two separate equations and two separate groups of variables. In the y direction, here is what your equation is going to look like. Everything is going to be subscripted in the y direction. Okay, but in the x, and here are the variables in the y direction. In the x direction, you've got this. You've got only constant velocity in the x direction, where the initial velocity vector is going to be equal to the final velocity vector. Okay, so they are the same thing both in the x direction. There's a little problem. This should be a sub y. This is a sub y times t. All right, let's try this problem. Here we go. So in this tutorial problem, you have a ball is thrown horizontally from a 13 meter high building with an initial speed of 9 meters per second. How far from the base of the building does the ball hit the ground? And here's a picture to go along with this. Okay, so we have written our equations and our variables. Okay, now let's go ahead and identify what we're having. So the units of this is in meters. So, and they're saying a 13 meter high building. So I think they're talking about it's 13 meters high. Okay. Now, again, just like in 1D motion, you want to make everything for relative to you. So if you're going to be the one throwing the ball, so you're right here, your height right here is 0, and that means it's going to fall below you by 13 meters. I know it sounds weird, just like it did back then, but it's going to be falling below you 13 meters. Okay? And it's thrown horizontally with a speed of 9 meters per second. So its velocity in the x direction is going to be positive 9 meters per second. Okay? And they want to know how far it goes in the x direction. So we're going to put our question mark right here. Now, at first glance, when you look at this problem, it doesn't look like we could solve anything. But we actually were given a lot of information, right? So we would need at least two numbers, another number besides positive 9, like a time, to get a displacement in the x direction. And we would need two other numbers besides negative 13 to get to solve for the other variables that we need here. Okay, so but we have to remember our concepts from over here. Whenever a ball is launched horizontally, its initial velocity in the y direction is 0. So all its velocity in the x direction, all of its initial velocity in the x direction was pointed to the right. Okay, So it has no initial velocity in the y direction. And what we also know is that the acceleration in the y direction is, if something is falling, is 9.8 meters per second squared down. Now, to do these types of problems, what I suggest is solving for everything. Solve for the time here and the final velocity in the y direction there, and solve for the time here, and then eventually solve for delta x. So we can only do one variable at a time, so we have to pick a variable to solve for. Let's figure out the time first. Let's figure out the final velocity in the y direction first. That means we don't have time. Okay, so and I just chose that randomly. But since time is in this equation, and this equation, we have to use this equation to solve for it. Okay, so I'm going to write this here. Actually, I'm going to get rid of those x's. So I'm going to need to do this again. V final y squared equals V initial y squared plus 2a delta y. All right, to find the final velocity, it's actually all set up for us. We're just going to square root both sides. V final y equals the square root of all of this stuff in here. And that's 2a delta y. Zoom in a little bit. Okay. And so what we're going to be finding out is just its downward velocity in the y direction. As if it was just falling, as if it was just moving in the y direction. We actually don't even care about what's happening in the x direction. So we're going to plug in numbers here. Square root is 0 meters per second squared plus 2 times negative 13 meters. That's going to save us, because this is negative. If we have a negative inside a square root, that would give us an imaginary number. And I don't like imaginary numbers. And incidentally, if you do get a negative inside one of these things, you kind of messed up. You might want to go back. It's most likely you didn't set your initial position at being at the top of the cliff and things falling below you. Okay, so the final velocity in the y direction is going to be 13. That's going to be negative times 2 times 9.8. Let's try that again. 9.8, that is negative, equals, and square root that. So 15.96. You know what? I'm just going to round up to 16. So 16 meters per second. That's how fast it would be traveling down. And since, so whenever you do squares or square roots, it removes the vector direction. So we have to go ahead and add that in here. So we know the speed from this is going to be 16 meters per second, but we also know it's got to be traveling down. All right. Since we have that, let's figure out time. The time, we're going to move our question mark here. We could use any of these equations to work with as long as it has time in it. I'm going to use this one because it's the easiest one. So V final y equals V equals a sub y delta t plus the initial velocity in the y direction. Okay. We've done this a million times. Not a million times, but we've done this a lot. And what we find out is that this is the result of the algebra to find time. So which is going to be negative 16, because again, this solved for the speed, we had to add the negative in there, minus 0 meters per second divided by negative 9.8 meters per second squared. Again, if you get a negative time, you might have made a mistake earlier. Just double check your work. So it's going to be 16, that's negative, divided by 9.8, that is negative, equals. So 1.63. So the time is going to be 1.63 seconds. Okay? And I will add that in right here. Now, why is solving for all of this stuff important, even when we're only supposed to find delta x? I don't like to be tricky. Where I already know how to do the problem and how to get to delta x. Once I have all my variables to work with, now I can start figuring some things out. Well, we know it's going to take 1.63 seconds to fall this distance, right? That means if it's going to get to here, it's got to fall 1.63 seconds, and it's got to also, it's going to take 1.63 seconds to move across to here, right? They're simultaneous. So it's falling at, it'll fall a total distance of negative 13 meters in 1.63 seconds. And that means for the ball to get to here, it's also got to move to the right a period of time of 1.63 seconds. So that means the time it takes to fall down is equal to the time it takes to move in the x direction, which totally makes sense. Now, to finish this problem up, you've got a delta x here, and that's going to be equal to the initial velocity in the x direction, which is also the final velocity in the x direction, delta t. So the distance it moves in the x direction is going to be positive 9 meters per second times 1.63 seconds. So that's going to be 9 times 1.63. 14.67 meters to the right. And there you go. So the procedure that we did, so you can see the procedure, we're going to write the 4 motion equations right here. And their variables. We're also going to write the x direction motion equation without acceleration right here. Because we're in free fall, there is no air friction, so there can't be any acceleration in the x direction. All right. Now we're going to read the problem. We're going to look for the units. Okay. So we're going to look for the units when we read the problem. We don't need to draw a motion diagram anymore, I don't think. And so we looked for the units. I read 13 meters high, so that told me that that was the height. So I had to go there. And it said it was thrown horizontally, and eventually it said speed of of 9 meters per second. Now I didn't know the direction, so I just make it moving to the right. And we had to also note that we were the one throwing the ball horizontally, so that means it was falling below us 13 meters. Okay, so what we had to do is we put our question mark here, what we ultimately had to find, and then we had to actually think about it and go, okay, well, it had no initial velocity in the y direction since it's thrown only horizontally. It's always accelerating straight down in projectile motion at negative 9.8 meters per second squared. And so what we did then is we solved all the y direction variables, and that helped us figure out what variable that delta t is, and that is transferable, and then we ultimately found delta x. So in these projectile motion problems, just solve for everything, because you don't know what they're going to ask you for follow-up questions in the homework. And it also gives you more tools to work with. Okay? Let's try another one. Okay? Okay. This one's a little bit different because it gives us time. So here in this problem, it's getting launched. We have, before we even read, we're going to write our 4 motion equations in the y direction. I got to correct that guy. That should be a sub y. And write our 5 variables associated with it. In the x direction, since it has constant velocity, where the initial velocity is equal to the final velocity, we have this. Okay. Now, once we've read it, let's go ahead and read the problem and pay particular attention to the units. Military shell is fired horizontally from the roof of a skyscraper. That artillery shell leaves the edge of the skyscraper with a velocity of magnitude, so that should just say speed. Physicists are horrible writers. Of 9 meters per second. After 5 seconds, determine the artillery shell distance from the edge of the skyscraper, which sounds like they're asking us to solve for delta x distance from the top of the skyscraper, sounds like that's delta y, and its overall velocity, so that is just v. And we'll talk about how to get that. Okay? Now, let's fill in what we have. So we know it's shot horizontally at 9 meters per second, so I'm going to make that moving to the right just as the picture shows. Okay? And I should be using black ink. And we know it's going to take a time of 0.5 seconds. And since the time it takes to go down, to fall down 0.5 seconds is also going to be the same period of time it's going to take to go across this distance delta x in order for it to get to right here. Or right here, wherever it's supposed to land. So we know the time of flight, which is going to be the same for the x direction and the y direction. So here are all the question marks we're going to need to solve for. Which overall velocity v, we don't have the overall velocity v, we're going to have to figure that out. Okay? So, let's do some stuff. Again, when it is launched only horizontally, all its velocity is wound up only in the x direction. That means its starting velocity in the y direction is 0. And since it's falling at free fall, its only acceleration vector is down at 9.8 meters per second squared. Okay. Now, let's try to figure out what we have here. Let's actually solve for delta y first. Okay, that means we don't have v final y, which means we can't use any of these equations. We have to use the top equation. So that is going to be equal to delta y is going to be equal to 1/2 a sub y delta t squared plus v initial y delta t. Okay? Let's just put in our values. This is going to be 1/2, and a is going to be negative 9.8 meters per second squared. Time is 0.5 seconds, or a half second, that we're going to square. The initial velocity in the y direction is 0 meters per second times a half second, which is just 0. So that's just 0. So we have this. Our delta y is then going to be equal to, get this, start with a square first. So I'm going to square that half second, which is a quarter second, times 9.8, which is negative, equals times the 1/2 in front, which is 0.5, equals negative 1225. So this drops 1.225 meters. Okay? So now we just figured out what delta y is. Negative 1.225 meters. Again, it's falling below you. So you're up here throwing things at people, and it's dropping a distance 1.225 meters, which I would categorically say that is not a skyscraper. Why? All right, you know what? Moving right along. Maybe it's a toy skyscraper. I don't understand what textbooks I get this from. Now let's solve for the final velocity in the y direction. Again, solve for everything because you don't know what you're going to need. And again, we're going to use the easy equation, and we're going to write it out just like it's written there. Ay delta t plus the initial velocity in the y direction. Eventually, after some algebra, which we've done a bunch before in the 1D motion stuff and just a second ago. You know what? I don't know what I'm talking about. It's already set up. Let's just go ahead and plug in some numbers. So the acceleration is negative 9.8 meters per second squared times a half second plus 0 meters per second. So the final velocity in the y direction, so that's a velocity in the that's falling at right before it hits the ground, is going to be 0.5 times 9.8, that is negative, equals negative 4.9. I probably should have known that. A half of that. Okay, so now we know this. All right, let's figure out the last question mark. Again, they have the same period of time. So this last question mark is going to be delta x. And again, it's set up for us, Vix times delta t. So this is a half of 9. So what is that? So this is going to be positive 9 meters per second times 0.5 seconds. So delta x is going to be equal to a half of 9. So is that 4.5 meters per second to the right? Okay. Cool. Well, we figured out delta y, which is what we're being asked to find, and we figured out what delta x is. Okay, now they asked us what is the overall velocity that is hitting the ground at. And I think that's what they intended to ask. It's hard to say sometimes. But here's what we're going to do. The overall velocity, again, is the addition of the velocity in the x direction and the velocity in the y direction. And we should be putting the final velocities. So this is v final x and v final y. They want to know what the overall final velocity is. Okay? Which is this. V final. So v final, so c squared equals a squared plus b squared. So v final y squared, v final squared is going to be v final x squared plus v final y squared, which will be then just the square root of both those sides. So Let's go ahead and figure this out. This is going to be 9 meters per second that we're going to square. We're going to square that right here, and it's positive. I'm going to put it in parentheses. I'm going to do this. Okay. Plus the velocity in the y direction, which was negative 4.9 meters per second, which we're going to square, and then we're going to square root all of that. Okay, well, I know 9 squared, it's 81. 4.9, I don't know what the square of that is, so we're going to, that's 24.01, which we're going to add that 81 to it. And negative 4.9 squared is going to be the positive. And now we get inside the square root 105.01. Now we're going to square root that 10.25. So the overall final velocity it's hitting the ground at is going to be 10 point, dang it, I had it. So 81 plus 24 square root, 10.24. That's right, 10.24 meters per second. Incidentally, if they ask for overall final velocity, they are likely to ask, which they didn't in this problem, which I'm surprised, is what theta is, at what angle it's hitting the ground at. Okay? And from our trigonometry review, to find this angle, we actually have everything. We have, this is going to be positive 9 meters per second. This is negative 4.9 meters per second. And what we figured out right now, this is 10.24 meters per second. We could use anything, sine, cosine, or tangent, but I like to use tangent of theta, which is going to be equal to opposite, which is, and we want the absolute values of these. So we're going to be doing this, the opposite of theta, because they just want the angle. They don't want to make it all complicated. They want to, the negative is going to pose a problem. V initial y, and we're going to do absolute value. So theta is going to be the inverse tangent of that. Okay. This is how I'm programmed to do these problems. You could use inverse sine, inverse cosine, since we have all the numbers. But why break from tradition? So this is going to be velocity in the y direction. Absolute value is 4.9 meters per second over 9 meters per second, and the units will all drop out. Meters over meters, seconds over seconds. So theta is going to be equal to let's do this. 9.8. It's going to be somewhere around a half. Oh, now did I say 4 point? Yep. It's going to be a half. Why did I close that out? So 0.5. And we're going to do the inverse tangent, which is 26.57. So the angle it's hitting the ground at is 26.57. degrees. Okay? Okay, so this was 3.2 projectile motion. Now there are 2 other parts to this series, and please watch all 3 as they are very helpful. Thank you.